First, I want to return the thanks to Miguel for being the man of the first hours, for having the idea of organizing this workshop. So Andrea quickly joined. And then we could also enthuse Stephen Brunton. And Alessandro gave us really this big forum. Without him, we would not have this, the largest audience of the von Karman Institute lecture series. Am I right? Yes? And I'm very happy to see so many people here interested, making the long way and interested in our field. And today I will give a course about analysis, modeling, and control of the cylinder wake. And I must warn you, it will be a bit of a tour de force. So I will quickly move through a number of methods. And I don't expect to understand all the details, but I would like to communicate why we are doing certain things and what is possible. So I would not, and today I will talk a bit about a Swiss Army knife of machine learning methods applied to an innocent-looking benchmark configuration. And I would not stand here if I would not be assisted by many smart students and colleagues, and the ones who have contributed to the lecture series here are, for instance, Guy Corneo, Makeda, Mnang Deng, and Daniel Fernet has contributed with a package for reduced order modeling. I will also present some results of Arthur Elert. And of course, we all work together with a couple of senior colleagues, Stephen Brunton, Marek Mosinski, Navid Nayeri, Richard Zeman, François Lusserang, and Luc Pasteur. And first, I would like to know you a bit better. So the language is mathematics and English, clear. Who of you is a bachelor student? Wow, 1, 2. Who is a master student? 2, 3. So it looks like 3, and maybe a couple of timid ones. Who is a PhD student? Okay, the majority, this is what I've guessed. Postdocs. And I see a couple of old people here. So who is professor and from industry? Good. So we have a pretty broad spectrum of people here. Now, who is in fluid mechanics engineering? The majority, as expected. Physics? A couple. Computer sciences? Good. So, so maybe you can teach us something. And so what I will assume that the Navier-Stokes equations are known, that the ordinary differential equations are known, PDEs and so on, linear algebra up to eigenproblems, elementary probabilities theory. So not that much. It would be good if you have some background in nonlinear dynamics, but this is not required. And briefly, a few words about me. So I started to study physics when most of you were not born. And then I had a couple of postdocs years in Göttingen, and we have already, with Dr. Rütten, we have a couple of people from Göttingen here right now. Then I was 2 years at the United Technologies Research Center, and this made a former physicist, a real engineer. It was a very formative period of my time. And then in TU Berlin, I became the first-time food professor. And then I switched to the CNRS. So CNRS is something like the Max Planck analog in France as a research director at 2 different institutes. I had a couple of affiliations. I name 2. And since last month, I'm professor at the Karman Institute of Technology. So we have written a couple of books. So the first book was Reduced Order Modeling for Flow Control. And the next book was Flow Control without Reduced Order Models. So to balance the story a bit. And first, I will talk a bit about the cylinder wake, the phenomenology. Then I will give you some brief introduction to what I consider as machine learning. And then I will apply the tools to the periodic wake. This will be very easy. POD, Galerkin. The transient wake will be very difficult, surprisingly difficult. And then I will talk about wake control using human learning, model-based, and wake control using machine learning. So machine learning control. And after the third section, I will make a short break, and you can ask a couple of questions if I don't forget. Maybe Miguel, you have to remind me. And so first we go to the cylinder wake. So this is the wake behind a mountain. You see a beautiful cloud visualization. Very surprising to see a wake, such a wake behind a very three-dimensional bottle. But in meteorology, this can be easily explained. I will not pause to do so. This is an oil visualization of vortex shedding. So here you see a harvested tanker losing its oil. So you can use a vortex street to track it. In the next slides, you don't see vortex shedding, but you see it should not be ignored. This is the unlucky Tacoma Bridge. So Tacoma committed suicide 6 months after the bridge collapsed. He became so famous with his bridge that he could not get another job. And of course, harvested tankers and collapsing bridges and cloud visualizations are not particularly reliable or environmental friendly and so on. So for our investigations, we need something much more simple to study vortex shedding, and we take the cylinder wake. So the cylinder wake is pretty well understood. It's based on the Reynolds number. So when the Reynolds number is smaller than 4, you have a single separation point. If it becomes larger, then you have a steady vortex bubble. The vortex bubble increases. At some point, you have a supercritical Hopf bifurcation. Oscillation starts. So this is the 2D vortex. Then you see 2D vortex shedding. And at a Reynolds number around 180, you have three-dimensional structures superimposing by the vortex shedding. But what is kind of surprising is the instability at the low Reynolds number essentially coins the coherent structures at very high Reynolds numbers. And maybe Xavier will explain some of these more. And of course, there's not only the cylinder wake. The cylinder wake is one of 5 classical types of flows. Here you see a jet, grid turbulence, again a wake, mixing layer, and a turbulent boundary layer. And the cylinder wake is the most simple one. So if a method does not work for the cylinder wake, you can forget it for all the other flows. And of course, there are many more flows of engineering importance, which are much more complex, and which can be typically considered as composed of shear layers, wakes, and these prototypic flows. So here you see some energy system and something for the production. But we will stay pretty much with a cylinder wake, and we have one example of a car. So now we go to a machine learning. And so you are here because machine learning is a very hot topic. And I try to boil it down a bit. I would say machine learning is essentially about solving regression problems. That means you have a function from A to B. And now there are 2 possibilities. Number 1, you have lots of data, pairs of A, B, and you try to fit a function. And number 2, you want to optimize a function, like a controller or something like that. In this case, you would need to test the performance of the function somewhere. And so the first kind of problems is essentially function fitting. There's something which is very easy, namely the interpolation. If you know the b values at these a values and you want to estimate the b values somewhere in between, simply do linear interpolation. Very simple. The method really does not matter. Now the next thing is more difficult, extrapolation. You have your database here, but you want to extrapolate the response a bit further away. And now you have several choices. For instance, you can say, I have a constant function, then you end up here. You can say I have a linear function, then I end up here. You can say I have a quadratic function, then you end up here. So extrapolation cannot be solved in machine learning. This is a very difficult problem. And when we are solving more the variational problems, if you have to identify a complete function. In this case, we can do some what is called exploitation. So exploitation essentially means we can do some gradient method. So we use the neighborhood of our functions or our parameters. And in some cases, we may not be confident that we are sliding down the right minimum. In this case, we need to do some exploration. Now, machine learning and AI is typically considered as synonymous, very similar. Actually, it is. So all of machine learning is part of artificial intelligence, but artificial intelligence has a couple of elements like natural language recognition or expert system, which are typically considered AI specific and not part of the machine learning part. And of course, a couple of very hot topics in machine learning are deep neural networks and reinforcement learning. So one was reinforcement learning was motivated by AlphaGo victory 2017, and neural networks are the core behind language recognition. And now we go to fluid mechanics, and I would say a lot of our fluid mechanics problems are regression problems. So let's look, if we want to find a closure relationship, so a function from the flow or the gradient of the flow to the Smagorinsky viscosity or some effective viscosity. This is one mapping. Another mapping, so this is what? Is it a variational problem or a curve fitting model? Well, typically it's a variational model because you don't have the direct connection. Next thing is you want to predict, you know the current state, you want to know the future state. So essentially this is solving ordinary differential equations or PDEs. You may want to do state estimation. So you measure certain hot wire signals and you want to estimate the whole flow field. And you have some data with the corresponding pairs. So this is data fitting. Or you want to determine a controller. So you measure something and you want to react on what you are measuring in order to optimize some cost function. For instance, reduce some drag or increase some lift or something like that. So this is a variational problem because if you know your response to one sensor signal, you do not have a complete controller, you cannot determine the cost. There's no notion of a local error. And maybe you want to do some parametrics. So from Stefan Goertz, we will hear about having an airplane, several Reynolds numbers, several Mach numbers, several angles of attack, and so on. And from a couple of simulations, we want to interpolate and perhaps extrapolate the performance at some other parameters. And there's something which is enabling a lot of these tasks, for instance, thank you. For instance, state estimation, you want to boil down, you have high dimensional data and you want to boil it down to something low dimensional. And so in machine learning, this is called an autoencoder. Essentially, you map the original velocity field to something low dimensional, and then you map the low dimensional vector back to the original data. So essentially, you construct the identity, but you go through a small throttle. So essentially, autoencoder is this. So PUD would be an autoencoder. Low-dimensional representations are autoencoders. And there's one part which you learn in machine learning, meta, how to avoid overfitting. So how to do the use validation data and training data wisely. So this gives you an idea about what machine learning is and how it could be used in fluid mechanics. We go now to the periodic cylinder wake, and we start a bit more first principle wake based. So now we want to have something like a low-dimensional representation of the cylinder wake. We could take, for instance, the steady solution here and some stability modes here, and then we have time-dependent coefficients. In this case, this marks the fluctuation, and this is kind of the basis. So in this case, we live on something like an n-dimensional space. And what is interesting, the Galerkin approximation here fulfills the most boundary conditions. If you have, for instance, a uniform oncoming flow, it's captured by that one. Then this flow will solve, these modes will solve homogenized equations. So for arbitrary coefficients here, you always satisfy the boundary condition for the original flow. So we would like to have such an expansion representing the flow being as compact as possible. And of course, it's most easy to come at the solution if you know the solution. And now we are assuming we have already a couple of data points. So this could be velocity fields here. And the idea of the PUD is to tune these modes to minimize the residual or to best resolve the largest fluctuation. So the first mode is in the direction where you have the largest variance in your data. The second mode is in the direction where you have the second largest variance, and so on. So this is a qualitative idea of the PUD, and you will learn more in today. Now, for the cylinder wake, it's rather easy. So now you get the mean flow here. These are the first mode, essentially the first harmonics with something like a minus cosine and a sine. So they resolve around 95% of the fluctuation energy. Second harmonics, they resolve another 4.9% of the fluctuation energy. Third harmonics, fourth harmonics. So essentially, the PUD mode does you a favor and does something like a Fourier analysis. So this is observed for a couple of flows, but there's no mathematical theory that this should always be the case, and there are also counterexamples. Now the next question is, when we know this expansion, can we build a dynamical system? And now let's forget a bit that we have data. Let's see if we can derive something interesting from the Navier-Stokes equation. So here we start with a, I think the battery is off. You want us already. Okay.
The switch.
So how many of those do you have?
Enough for a few hours.
Okay. Good. So what is easy to see is when you have the look at the Navier-Stokes equation, that there should be one term which corresponds to the time derivative. For something like a linear viscous term, you should also have something like a linear Galerkin term. For a quadratic term, you should also get something like a quadratic term. It's a bit difficult to see why you should get for a pressure term another quadratic term, but you can see it from the pressure Poisson equation. Now, how do we arrive these things? But first, we need something like an inner product. So the inner product is defined here. You integrate over the volume the velocity fields with an Euclidean inner product. The PUD has orthogonal modes, so this simplifies some terms. And now we make a Galerkin projection for the first term. So we multiply this with a mode and integrate this over the domain. So this is the first term. Now we put in the expansion. A0 equals unity, so that we have this expansion. So this can be cancelled, and then we can pull some the coefficients out and take the derivatives and so on. At the end, we have this term, and with the same method, we can also derive all the other terms. So this is the Galerkin method in a nutshell. And probably you ask yourself now, does it work? Yes, it works beautifully. So the data here corresponds to the simulation. So this is A1, A2, so the most dominant modes. And the circle corresponds to the Galerkin model. Beautiful agreement, and we should be happy. But you change a bit the viscosity, and you change the viscosity, the Reynolds number from 100 to 80, and you get to the fixed point. You change the viscosity from 100 to 120, and it explodes. You look at the transient, and the transient are 20 times longer than the real transient. You look at this point here, and it's a mean flow, not the steady solution. So we are a bit in trouble. So we have a beautiful model, but it has a very narrow range of validity. And now we go to a more complex problem, the transient wake. So we look now at one quantity of the cylinder wake. Let's take the lift. And we start close to the steady solution, where we see some stability modes originating. So initially, the lift is steady, and at some point, it starts to oscillate, and then we go to the limit cycle. So we see the typical ingredients of a self-amplified, amplitude-limited oscillator. And when you also take the derivative of the lift coefficient, then, oh, I wanted to let you ask some questions after the search. So, do you have questions so far? Is this good or bad? Does it mean everything is clear? Oh. Now, the interesting stuff comes now, transient wake. So we look at the, some sensor signal, for instance, we look at the lift coefficients. If we take the derivative of the lift coefficients, then we get a clear imprint of something like a Landau oscillator. And looks very easy, but there's some trouble. And the trouble is if you look at the modes, initially we have something like stability modes. So this one here corresponds to this mode. Here we have the stability mode. So there's already a significant change from the patterns as you go from here to here. And when you are on the limit cycle, the fluctuation level goes further upstream. So somehow we see already it should not be possible to put it in a simple Galerkin framework. So what we really have is a situation which is depicted here. We start at the steady solution, so this is the steady solution. Then we move outwards on a plane, so this is the real part and the imaginary part of the most amplified mode, the only most amplified mode. If you would stay on this plane, this would go forever. So linear stability analysis cannot explain the amplitude saturation. So what happens? Well, we have a nonlinearity. More precisely, we have a Reynolds stress. And the Reynolds stress changes the base flow. So as the fluctuation moves more and more up, the mean flow becomes shorter and shorter. So this bubble is eaten away by the Reynolds stress. And this change of the bubble from the steady solution to the mean flow is communicated by essentially something like the difference mode, which we call the shift mode. So essentially it points from the steady solution to this mode. And essentially it's a reverse flow. So if you have a reverse flow here, sorry, then it's a forward flow. Reverse flow here, you add a forward flow and then you can reduce this bubble. So there's a linear relationship between this amplitude and the bubble length. And so you start here, then the base flow changes. At some point you end up on a limit cycle. The limit cycle has a different base flow, and the PUD mode now characterizes the first harmonics. Now, if we build the Galerkin model, and the Galerkin model only contains this data, we only span this plane, and essentially this plane is neutrally stable. So we cannot capture the amplitude growth or the decay, at minimum, not realistically. And in a second, I will show you how we can derive the equation for the amplitude motion, more precisely the Reynolds equation. So I will return to this slide shortly. So what are the most relevant modes? The most relevant modes are related to the first harmonics. We can take, for instance, the first two PUD modes. And there is a base flow change. So this is something like this shift mode. Now we have three modes. And the basic mode is a steady solution. If now the expansion has three modes, is shown here. And the dynamical system after the Galerkin projection should look something like that. So it has a linear term, it has a quadratic term. It cannot have a constant term because if you put in the steady solution in the Navier-Stokes equation, then you have A equals 0. So A equals 0 must be a fixed point of this dynamical system. And now if you assume that the mode number 1 and 2 are oscillatory, that means A1 and A2 are something like a sine and cosine, and the third mode is slowly varying, so this corresponds well to what we find in the simulation. In this case, you would be inclined to make polar coordinates. So there's an amplitude and a phase, and if you expand the amplitude with this Galerkin expansion and the phase with this Galerkin expansion and also the shift mode amplitude, then you get these terms plus higher harmonics. So for a uniform rotation, the higher harmonics would vanish And essentially, this must be somehow the dynamics of the flow. So this is one of several ways of deriving these equations. Now we have again the Galerkin system, this Galerkin system with a higher harmonics. Now we observe that the growth rate is much slower than the damping rate of the third mode. So wherever we start, we quickly move to this mean field paraboloid. We can neglect this derivative. That means A3 is slaved to the square of the fluctuation level, and we move on something like this paraboloid. Now, if we insert essentially this paraboloid back into the original equation, then this one becomes the Landau equation. So we have a linear growth rate and a cubic damping. So when I looked in Landau-Lifshitz in my student time, I was very surprised that the quadratic nonlinearity can give rise to cubic damping, but you can only get higher order damping at the moment you have a manifold. So essentially, if something like R squared, a second order term is linked to a first order term. And so here you see the cubic damping. You also see that the frequency changes. Typically, the higher the amplitude, the smaller, also the higher the frequency. So this is how we now arrive at these equations. And back to this equation, this is essentially our state space picture, which we should have in mind. Now, there is probably for many people, it looks like a lot of things have been hand-cooked with a lot of physical insights and assumption and so on. The question is, can you somehow distill the paraboloid more automatically, in an automated way? And the answer is yes. And the key idea is called locally linear embedding. So who of you has heard about it? Okay, Laurent, Guy, Scott, the senior people. So the basic idea of a locally linear embedding is that there are a lot of, all the data may live on a low-dimensional manifold, and if it lives on a low-dimensional manifold, you can see it here, you would like to have a mapping from something of the dimension of the manifold to the original data set. So here we have an S-shaped original data. We generate some data points here, so they're a bit noisy to essentially test the robustness of the method. And now there's a method which creates a mapping from some feature coordinates to the original shape. So here, what did we gain? Here we go from 2-dimension to 3-dimension. We did not gain much, but we can do the same also, of course, from 2 to 4, from 2 to infinity. And I will explain the algorithm later when I talk about reduced order modeling. So this is an appetizer. We apply it now to the cylinder wake. And for the setting, we take some, here you see the fluctuation energy over the time, steady solution, average flow. I'm talking about results of Arthur Ehlert. So we take essentially the data from the beginning of the oscillation to the limit cycle. So close to 1%. This is I think 50%. This is 100% of the fluctuation level. And we take something like 16 transients, 1,000 snapshots each. So we have a lot of transients at this moment. And when we do this locally linear embedding, we get something very interesting. Essentially, we get these coordinates. This is, let's say, gamma 1, gamma 2. This point here corresponds to the steady solution. These points here correspond to periodic vortex shedding. As a point in the neighborhood of the steady solution, if I pick this point and look which velocity field this corresponds to, here I see the stability modes, here I see the intermediate modes, and here I see the limit cycle. So that means in an automated way, I can distill a two-dimensional manifold of the original data, and the error is something like 1%, which is probably the numerical error. So all the data lives on a two-dimensional manifold, as we could have expected. Now the question is, we know we will learn PUD expansion, DMD expansion, and so on. What do they give? We take the transient data. So this is the first PUD mode, second PUD mode, vortex shedding, nice. This is the shift mode, essentially the base flow variation. Now we see a mixed mode. Then we see something like which corresponds a bit like to the second harmonics. Then we see a mixed mode, and then we see some other mixed mode. So the PUD modes are not frequency pure, and they don't have to be frequency pure. If you look at the amplitudes, they are, the first three behave like in our essentially mean field model, our least order Galerkin model. Then we have some intermediate mode, so it looks a bit ugly, not very good. Now you can say, why did you take PUD? And I'm talking now for the experts, and why didn't you talk about DMD? Well, we did DMD. So these are the most pronounced DMD mode. The first one, the second one, the third one, essentially these have slightly different frequency, the other one. So we take the DMD mode, which contribute largest to the expansion. So essentially everything looks pure here, so it looks much nicer. Now there's of course a little but. When you do DMD, you have a linear framework. Essentially your expansion of the first mode will look something like that. You always have then, you have oscillations which are either increasing or decaying. That means if you would now extrapolate things right on the limit cycle, of course you will get wrong results. If you go left from your data region, you will also get a wrong result. So the DMD can be very good if you are in the linear regime. It can be very good when you are on the tractor, but they're not particularly well suited on the in the transient regime. And then we have made a switcher between both, which we have called recursive DMD. I will talk about it later. What we essentially do, we require monochromaticity of the modes, but we found a trick to make these modes orthogonal. And then we essentially get near the similar resolution like PUD, but we have a pure frequency behavior. So these are the corresponding amplitudes. The first three look as we expected. Then there exist some intermediate modes, and the other modes essentially contribute to a shape deformation and to higher harmonics. If you look now at the residual, so here you see the fluctuation residual. 1 means 100%, so you don't resolve anything of the fluctuation, and you go down 2 decades. If you look at PUD, of course, it becomes increasingly better, but for a 1% energy error, you need 50 PUD modes. So you have to let this sink. You have a two-dimensional manifold, and you need 50 PUD mode for a 1% energy error, and a 1% energy error is a 10% amplitude error. So PUD is something very nice, but may not always be the best thing to do. So this is essentially a credo that manifold models, you should consider manifold models. With a recursive DMD, we sacrifice a bit accuracy. We are not much worse, and we get a bit purer modes. In terms of the resolution residual, DMD modes are not very good, as expected. Questions so far? It's a good point. So the question is, what do you lose when you do LLE? And essentially, you lose nothing. If you are on the limit cycle, you can multiply the limit cycle with cosine phi, and then you have something, one POD mode with sine phi, and then you have the other POD mode. You can multiply it with cosine 2 phi, and you get the second harmonic, sine 2 phi, and so on. So essentially, you get all the POD modes, and if you, by the same argument, you can also get all the DMD mode, because essentially the DMD mode and the POD mode are both Fourier mode for the limit cycle. And so I would say the locally linear embedding is a generalization of it. Now, at some point, you may say, I'm cheating a bit, because we live on a two-dimensional manifold, but how is a two-dimensional manifold characterized? Well, we have 16 transients and 1,000 snapshots each, so we have something like 16,000 snapshots which characterize this manifold. So that means the data load on the reconstruction of the flow is very high, but still, the dynamics is two-dimensional. And there's a big difference between 2-dimension and 50-dimension. In 2-dimension, you can build a dynamical model, you can make an estimator, you can do a control, you can do everything. If you have 50 modes, essentially you just have a noise generation. With 50 modes, it's next to impossible to calibrate it and get a good prediction, do the control design with it, do the dynamic estimator in it, and so on. So sometimes these manifold models can be a real enabler. Any other question?
Yeah, I can ask a question about where you did the projection of the Navier slopes on the modes. What did you do with the pressure term?
Very good.
Did you ignore it, or you have separate modes for the pressure field? Just wondering how you did it.
So in this case, I've ignored it when I had a large domain. So when I have something like 15 diameters, then the pressure term is rather small. But the pressure term becomes very relevant if you have a short domain. If you have something like 6 or 7 diameters, then you have to include the pressure term, because the pressure term is either an energy source or an energy sink. And now the question is, how do you incorporate the pressure term? Now there are many possibilities. And you have alluded to one, namely you do the POD of the pressure field, and you put the pressure field in this Navier-Stokes equations, and you have one system of equations for the POD mode amplitudes for the velocity field, and you solve the other coefficients with the pressure Poisson equation. This is one possibility. Another possibility, actually, you can derive. You can derive an accurate pressure term representation for the POD modes. So this is what we did 2005 in 1JFM. This is another possibility. So if you ask Angelo Iollo, so Angelo Iollo essentially calibrated an extra term in order to account for the modeled pressure model. It turns out that in many cases, the additional terms which you have to add because of the pressure are just linear. I can tell you a couple more approaches, but I think this is now very interesting for you, but not for the big audience. So, last question. Good. Then we go to the next thing, control. So, when you do analysis, so analysis is always very easy, because when you get dead data, you can always make a plot y over x, and the data cannot complain anymore. If you do dynamical modeling is a bit more difficult, because in the dynamical model you want to predict the future, and maybe you do not know the future. So you have an element of cross-validation. Now, at the moment you do control, you have a much worse situation. So essentially, you want to predict the future, but not only the future, the unforced future, but the future for many different actuations. And this is a very hard business. And in most of the cases, you will not have enough data for this type of control. So first, I will show you a case, the cylinder wake, of course, where we have this data. And the task is as following. So we cannot build the controller based on the Navier-Stokes equation, because if anything is larger than 10-dimensional, then the control methods typically blow up or become very difficult. So we would like to have a low-dimensional model of our original plant. So here you see the plant. B is our actuation signal, and S is our sensor signal, so it's sensor-based feedback control. We don't want to do it with the original plant, with the Navier-Stokes equation or the experiment. We want to derive a model before, and once we have the model, determining a controller is easy, and then we copy this controller from our model in our original plant. And the goal is always to optimize some performance, J, so essentially the model also must give the performance, let's say drag, lift, whatever, which we eventually measure. So now the task is build a model which contains the state and the actuation commands. You need some measurements equations, and from this derive a controller which only rates on what you know, namely your sensor signals. I will talk about the right-hand side later. So the right-hand side is kind of a shortcut, which is emulated in natural fluid mechanics. So here we go again, back to the cylinder wake. We have discussed this, and typical control problem is stabilize, so essentially reverse the Hopf bifurcation. Now we are at Reynolds number 100, the critical Reynolds number is something like 42, way above, lots of fluctuation. We want to go back to 0, and we assume now something a bit academic. We assume that we have something like a volume force here. So the volume force